Hello everybody. So welcome to this lecture number 3 of week 8 on the course on linear systems theory. So we were talking in the last 2 lectures about the way we define the concept of observability, why we need the concept of observability and so on. So we will have this short lecture just to understand the discrete time analog of the observability, and most of the steps will be very similar to what we did in the discrete time systems for controllability analysis. So I would skip much of those steps here, so they might just be redundant to write those all over again, and we will equivalently try to derive the eigenvector test, the PBH test, and so on. So what I know now is the concept of duality, right? That if A, B, so we had a system written in A, B, C and D, and A transpose, C transpose, B transpose and D transpose, and then we had some relation between controllability of one system with the dual of it, and then observability of one system and the dual of it, right. So we will make use of that results to derive the remaining tests for control for observability. Okay. So we start with discrete time systems. The discrete time case, well, everything is looks pretty similar. So I have xk plus 1 is ak, xk, bk, uk, and so on. Similarly, for the output. Again, so the way we construct the solutions via the variation of constants formula by defining the discrete time state transition matrix, I just substitute for the output that y of k looks with c of k, phi t, t naught, x naught, and then the bunch of terms here. So we did derive this in one of our earlier lectures. Okay. So the definitions go very similar to the continuous time counterpart. So given 2 times k1 and k naught, the unobservable subspace consists of all states x naught for which like this holds, right. It is very similar to what we had earlier, and similarly the unconstructible subspace consisted of all states this one. So the definition of observability and constructibility still remain the same. Okay. So similarly in the case of discrete time controllability, there is a little distinction that the notion of reachability and controllability were same for continuous time LTI systems, but the discrete time equality required some extra conditions on the matrix A to be invertible, right. So similar results hold also for the observability test for discrete time systems. Okay. So the definition of discrete time system requires a backward in time state transition matrix from k1 to time k, right. So and then this matrix is defined. So xk1 is defined with xk. So this can be solved for xk if and only if all these a's are invertible, or all these a's are non-singular. Otherwise the unconstructible subspace cannot be defined if this condition is not met. Again, I'll skip the steps here, but you can just refer to lectures on week 7 for controllability. It will be exactly the same. Okay. So again, when is the system observable? The system is observable even in the discrete time when its unobservable subspace consists only of the 0 vector, and similarly if it is constructible if its unconstructible subspace contains again only of the 0 vector, right. So this is the very similar definitions to what we had before. Okay. So when this holds, we will first try to construct an equivalent of the Gramian for discrete time systems. So I just define my Gramian here. The observability Gramian, again depending on phi, C transpose, and so on, right. So again very similar to what we had seen earlier, and the results also translate beautifully here that given any 2 times, the unobservable space is just the kernel of the observable Gramian, and similarly the unconstructible space is just the kernel of the unconstructible Gramian. It is so. Again, we can prove quite easily. Of course, so the rank based conditions still hold, right. So, where the system is observable if and only if this rank of WO is n. Similarly, the system is observable if the rank of WCN is n. Okay. So, nothing changes here. Similarly, I can do the Gramian based construction. So, having known the Gramian, how do I construct the state? It again starts from the definitions over here, and then using the Gramian, I can just write down this this expression here, right. This looks very similar to what happened in the continuous time case. Loosely speaking, just the integral replaced by summation here, so to speak. Okay. So, these are all just plug and put it over here, and they all translate quite beautifully, except one condition of equivalence between unconstructible and the unobservable space, or the equivalence between constructibility and observability. Okay, right. Similarly, I have a Gramian based reconstruction for the constructible case. Okay. Now we go to the observability tests. So, first is the rank based condition, right. So, if I look at so I will just do the derivations from the duality thing. So, from the duality theorems, it is known that the pair A comma C. Okay, from the duality theorems, we know that the pair AC is observable if and only if the pair A transpose C transpose is controllable. Okay, so what was let us write down the dual system here. So, I have X say tilde dot is A transpose X tilde plus C transpose some U, Y tilde is B transpose X tilde plus D transpose U tilde. So, whenever this system is observable, it is equivalent to saying this system is controllable. Okay. Now, how do I derive the observability conditions for this system based on the controllability properties of the dual system, because I know that observability of this system is equal to the duality to the controllability properties of this system. So, what do I know? That the rank for controllability in general is that the rank B AB till A n minus 1 B should be n. So, this is the controllability matrix, the rank of it should be n. Okay. Similarly, now I can define the controllability matrix for this guy. So, the controllability matrix for this guy would have C transpose, A transpose, C transpose, and so on. A transpose n minus 1 C transpose, right. So, this will be the controllability matrix for the dual system will be the observability matrix for the original system. Okay. So, I just then write down the observability matrix in this form, right. So, the observability matrix just translates to this one. Okay. And then therefore, I can conclude that the observability for the pair AC is defined as this is the transpose of C, right. So, if you just look at the definition over here, or the way we derive the observability matrix here. Okay. So, observability matrix is now defined in this way: C, CA, CA square, and so on. Okay. And then the system is observable if and only if the rank of the observability matrix is n. Okay. So, we start with the example that we had in the first lecture, right. So, the question there was, is it possible to develop a controller where the control law is some function of the states x1 and x2, and the control law is say updated at some every interval t. Okay, so this and then what I have for measurement is only the output y here. So if I write down the state equations for this, so I will have something like this, where y is just as this one plus some d here. Okay, so I just look at the observability matrix, which is just given by C. So this is the C and then the A times C. So I can just look at this matrix and say that the rank of this is not equal to 2, it is actually equal to 1, and therefore the system is not observable. And therefore the problem here, which says can I develop a control law which is based on this present states and then and the control is is updated as an interval t, such a controller, well, is not possible, as the initial states cannot be determined, right. So because the system is not completely observable, right. Okay, so now some tests which are very similar to what we did for the controllability. So the first result says that the system 2 is observable if and only if there is no eigenvector of A in the kernel of C transpose. Okay, I will not do the proof of it, but I will explain you this with the help of the duality concept. Y of t is C x t d u t, and then have the dual system A transpose x t B transpose some u t y, the new output is sorry, this will be C transpose, then y will be B transpose x t plus d transpose u t. Okay, so this system is okay. I am looking at the observability of this system, and this is related to the controllability of this one, right. Okay, so what is controllability here? So controllability would say that there is no eigenvector of A transpose in the kernel of B transpose. That was the controllability for this system. Okay. Now, what about observability of the system? The observability of this system is equal to saying controllability of the dual system. Now, let us write down the eigenvector test for the dual system. So, analogously, the system is controllable if and only if there is no eigenvector. So, this A transpose here becomes A in the kernel of C. This is the eigenvector test for controllability of the dual system, and this condition is exactly equal to the observability of the original system, and therefore I can say that the system, this LTI system 2 is observable if and only if there is no eigenvector of A in the kernel of C. Like okay, I can do a constructive proof the way we did it in the previous one, but then since we already know the duality, we can just make use of the tools there and then exploit the relationship between the controllability of the system with the observability of the dual system and so on, right. Similarly, I will have the PPH test. Again, I will not do the proof of it, or you can just write down the analogous thing for yourself. The LTI system 2 is observable if and only if this rank is equal to n. Again, I will not touch upon the proof or even with the duality. I would like you to work on it a bit. Similarly, if I have that A is a stability matrix, so I am looking at the equivalent of the Lyapunov test. Assume that A is a stability matrix, the LTI system 2 is observable if and only if there is a unique positive solution W to the Lyapunov equation, this one, right. Moreover, the solution is given by these two here. One is, this is for the continuous time, this is for the discrete time. Again, they look very similar to what we had in the case of controllability. Again, all these derivations you can just do by exploiting the duality relationship between controllability of a system and the observability of the dual system, and vice versa. Okay, just for your own benefit, or just for a little more learning, you can write down the proofs starting from 0, right, assuming that you do not know the relation between the duality, you do not know the duality relationship between controllability and observability and so on, right. It will just help you to kind of get more and more familiar with proof techniques. I will not do that here. I will just leave that to you for some of your own learning, right. And if you have any difficulties, you can always post that in the forum, and we will be more than happy to help you out. Okay, so that concludes today's lecture. So next lecture we will look at the observable decomposition, very similar to what we had done in the case of controllable decomposition, and then we will have a weaker version of observability called detectability, which is again you can relate it to stabilizability, which was a weaker version of controllability. So that's coming up next. Thanks for watching.